And with that reminder, we'd like to get started with our first speaker, Brian Milbrath from Pacific Northwest National Labs. And Brian, your talk should be queued up here for you momentarily.
It's good to be here in Vienna. Good to see you. It was interesting this morning, one of the keynote speakers mentioned machine learning for radionuclide analysis, and I get to talk about my first foray into trying to do that, along with my two data science colleagues at PNL, Alex Hagen and Christian Svinth. I have a clicker. So the IMS produces a lot of interesting data, and the quality of that data is very important. It can be corrupted or have just noise issues, detectors degrade and so forth. And so some way to automatically monitor the quality of that data is needed. And this was kind of a case study of ours based on particulate spectra data from IMS to see what machine learning could do in that regards. And shown in the slides are several spectra there. The gray one is kind of the average spectrum for this Canadian station, and then the orange ones are various, very different spectra from the average from that station, many due to electronic noise or something. So for our study, we use supervised learning. That's where the machine learning, the network is trained on labeled data. We used 5 years of data from 29 stations at over 200,000 spectra, 80% for the training and 20% then for the testing. One of the very first things we had to do was get all the spectra to have the same number of channels. And of course, the goal in your training is to minimize the difference between actual and predicted values of what your resulting network. It's interesting, the data scientists, the first thing they did was they trained their network to predict the location on the globe given a spectrum. And so the network produced a location on the globe that minimized the Haversine or Earth surface distance from prediction to real location. And then I said, well, of course, all we really need to do is pick the right station. We don't have to pick the exact location on Earth. And they did a second pass where they came up with a classification system done with cross entropy, which is measuring the distances between two probability distributions. We used 3 types of neural networks. Multi-layer perceptrons are ones where your neurons are fully connected. In other words, you have information immediately connected from one channel to every other channel. Much less computational is the convolutional neural network, which is good at learning features. You could view it as kind of filter optimization is how it operates. And the third type is a newer machine learning approach called transformer, which is useful in that you can have different numbers of channels, because what the transformer does is it groups data and moves on from every single channel. But in truth, the results, because the truth is IMS spectra are very rich data set with a lot of easy ways to come up with what statisticians call distances, that we got good results no matter what neural network we used. Greater than 95% of these location predictions were within 150 kilometers of the true location, which of course was a station, and greater than 97% of our station classifications worked with this supervised training. This matrix may be a little too small to see on the screen, but the x-axis are the predicted stations and the y-axis are the true stations, so everything on the diagonal is correct. Everything off diagonal is miscorrect. What's interesting in this picture, and the scale on the off diagonals goes from 0 to red or purple. The largest misclassifications are in the order of 5-6%. But what's interesting is, and it's probably too hard to see, a lot of the misidentifications are, I don't suppose I have a laser, no. A lot of the misidentifications are like one Canada station for another Canada station, or one Russian station for another Russian station, or one Canada station for a US station. So, and it's a little harder to see, but polar and polar on the two ends of the Earth. So there's clearly some local climate factors that come into play. Every spectrum on this slide is a misidentification. In terms of entropy, the ones at in the top rows, the lighter ones, those are higher entropy, Shannon entropy predictions, which means a lower confidence prediction. And so what you see there when the network had low confidence were things like electronic noise and so forth. It had low confidence in prediction because lots of stations have electronic noise. Your ones at the lower extremes where you had low entropy predictions, which means more confident predictions, tended to be things like a new nuclide showing up in a spectrum or so forth. It would get things, it would be confident about its identification, but wrong because these were things it was seeing less often. Just to take a closer look at the mispredictions. So, for example, Canada 15 there, CAP 15. The orange represents its average spectrum. And the gray is the average misprediction when it's confused with Canada 16. And all of these represent ones where you had at least 10 mispredictions of one station to another. And so what you're seeing is when Canada 15 gets more active, it starts to look like Canada 16. Or when US 76 starts to get a little less active, it starts looking like Canada 17. Again, your neighboring stations seem to be somewhat related, and that's when they start getting confused, is when something changes that makes them look more like another station. So given that initial study, you could start to maybe think about how you could operationally do some anomaly detection with machine learning. You could use machine learning to automatically detect things like data quality issues, detector issues like the gain is shifting, or interesting things where the station is activity is changing. It's seeing nuclides that it doesn't normally nuclide. I think with a little more work, there's some interesting thing there in regards to, because of this note, are seeing that neighboring stations were often seeing confused with one another. I think with some study of connecting to ATM and climactic regions and so forth, there will be some further interesting things. For example, when these two stations, the Japanese station and the Russian station, look alike or confused, maybe that represents periods when strong fronts, we didn't look into this, but I think it's an area of study, when large fronts go across Asia, or perhaps when the particulate load in the atmosphere due to things like Siberian fires is generating a lot of similar activity. Things like that, I think, would be interesting for further study. So supervised learning is ideal for easy tasks, and to operationalize it, you would need to come up with some metrics. So, you would want to pick your false alarm rate you're willing to live with, that you're going to investigate things. Dimension reduction would help because of this issue with different channels for different detector types. And an important thing is you have to, figure out how you're going to retrain if you use supervised learning. Because if something substantial changes, like a new detector or something, you basically have to start over with supervised learning. And that's why when you put machine learning into operations, in most cases you wind up using what's called unsupervised learning. In unsupervised learning, you do the appropriate dimension reduction to handle those things that regularly change in your system. And then you can do things like two-sample tests or other statistical techniques on your reduced dimension space to better operationalize your automatic analysis. And of course, in truth, you can also use machine learning can guide signature discovery. We saw some interesting things just in this little study of ours. But truthfully, some of the things we saw as anomalies, you don't need machine learning to figure out, right? You know what a noisy electronic noise spectrum looks like, but machine learning can help you identify issues that you have, and then you could go to non-machine learning techniques easy enough to automatically detect things like electronic noise and so forth. So in conclusion, particulate spectra in the IDC sometimes have anomalies. Those can be electronic noise, reporting issues, or some other mistake. Assuring the authenticity and quality of data is critical to the IMS's performance. There's a lot of information in there. We found it relatively easy to apply machine learning to it. Supervised neural networks can predict the I expected to be able to find anomalies. I did not appreciate how good we could do at picking the correct station of an IMS spectra. We got greater than 97% of being able to classify the station that an IMS spectra originated from. And those mispredictions were often indicative of some interesting anomalies. So I think the spectra are ripe for further work in machine learning and ultimately operationalizing the technique to help in automatic analysis. Thank you.
All right, thank you very much, Brian. Does anyone in the audience have any questions for our speaker? Please.
There was.
It's coming. Matthew.
Thanks, Brian. Nice talk. For classifying the station location, was it all done kind of independently, or did it go in a batch mode of saying, okay, let me bin these stations with the right spectra, or was it all? Well, they could be anywhere, I guess. How did you do it?
So, the data was all labeled, but then it came up with, in the case of the classifier, it came up with, the network would come up with 29 values for the 29 stations, and that the one with the lowest entropy value, which kind of represents, you could think of that as comparing two probability distributions. It would pick that particular station for the classifier. If that answers your question, okay.
Okay, thank you. Any other quick questions for our speaker?
Thank you, Brian. Our next speaker